Hello, my name is Matthias Springstein. I would like to present you our work Visual Narratives Large-Scale Hierarchical Classification of Art Historical Images. To give a short motivation why it's a challenging problem and why we are working on it, I would like to introduce you to the Iconclass taxonomy. Iconclass stands for Iconographic Classification. It's an annotation schema that includes several thousand concepts from historical events, the Bible, and the literature. It's very common in Art Historical Institute and museum, but it requires expert knowledge to annotate an image with the schema, and so it's very time-consuming process. Therefore, this annotation schema is only active annotated by field institutes, which slow down the indexing of large-scale art historical archives. To speed up this process and improve the distribution of Iconclass, an automatically image annotation system would be very helpful. And here in the slides, for example, we see some annotation examples for the image Elders Last Super. They have two annotations. First one with level 5, Last Super, and the second one 4.1c3 and late table with a depth. When we now go to our main goals of our approach, the main goal is basically we want to develop an image classification system to predict Iconclass depicted in a single images. And to do that, we want to leverage the hierarchical structure of Iconclass notation schema that in our case contains more than 20,000 different concepts, and the taxonomy that goes down to a depth of level 10. And additionally, we'll also make use textual meta information that's available in the Iconclass system for each of the individual notation, like keywords and text descriptions. And with that, we want to make an image text cluster pre-training to improve the performance of our system. To achieve all our goals, we want to create a new large-scale Iconclass image data set. For the first goal, the contrastive image text pre-training is the first step in our pipeline. We synthesize image text pairs based on one or more Iconclass annotation per image. We consider three different strategies to do that. The first is KW, where we basically concatenate all the keywords that we get for all the annotations in the Iconclass annotation schema. But sometimes this behaves a not natural description. When you look at clip, for example, this is more natural description that you can find there. So to solve these problems or to see if this is a problem, we also consider GPT and blip. GPT is basically only a language model that generates a summary given a set of keywords, and then we have blip, a vision language model to synthesize captions based on keywords and now also the. When we have synthesized this text description, basically we optimize clip to minimize the difference between images. For the next concept goal, the iconographic concept classification, we propose our hierarchical cross-attention transformer called CAT. Then vision transformer as an encoder, and then we have a normal transformer as a decoder that is modified for hierarchical multi-label classification. Here the input basically is the embedding of the parent higher level node, and then at each iteration we predict only a branch of the taxonomy at a specific level, and the output is not a softmax function, but in our case a sigma for multi-label classification. Go more into detail how training and inference work. Training is done is for each of the image we select up to n notations per image. And then for each of the notations, we generate a sequence based on the Iconclass notations. For example, on the second slide, you see our two Iconclass notations. And here, for example, concept 4.1c3 comes to a sequence start token 4.1c3 and the stop token. At the end, we make one encoder forward step, so the image goes in. We make it a forward step of the encoder, and then we multiply the batch size and make n decoder forward steps for each of the sequences and optimize output. For the inference, we handles a little bit different. Here we basically select the node with the highest probability that has not yet been computed. In the beginning, basically this is the start token that we feed. Then we get the embedding, feed it to our decoder and decode the first branch. Then we repeat this process until we couldn't find any concept with a higher probability above a specific threshold. Okay, now to the data sets that we consider during our experiments. We have two data sets. The first one is publicly available in Hugging Face, contains around about 19,000 images, 360,000 icon class annotations for these images, and it considers 12,500 unique icon class. Then we have the Icarus dataset with 480,000 images, 1.3 million icon class annotations, where 20,600 of them are unique. For the image processing, as you can see on the right side, it doesn't only contains the images, but also more information that could be a problem for the classification. So we apply an image segmentation method to only get the relevant part, and then we create a new image based on a 2D packaging algorithm. For the experimental evaluation, first part is the contrastive pre-training. We want to see what is the impact of the different strategy, and we also want to compare if he doesn't what is the difference if he doesn't make any contrastive pre-training evaluation. This is basically line of 400M in this table. After the pre-training, we train our CAT classifier on top and measure the mean average precision score on the test data set of these methods. To get a more insight of our models and the behavior, we also consider different kinds of subset. Basically, the first one is the entire class dataset, and then it becomes smaller and smaller depending how many training examples we have during our training purpose. So you see the last column is basically if we have more than 1,000 images per concept. And the first outcome is basically that you can see that basically contrastive pre-training mostly helps for concepts that only have a few examples, so the very rare concepts basically, then it's very helpful. And we can also see that Blip outperforms all the other strategies and also the baseline model line of 400. When we now go to our classifier, we consider here the dataset Ikai first, and then here we use two groups of classifier. The first one doesn't use the taxonomy at all, so clip zero shot, for example, or flat is basically 20,000 classes predicted without considering child and parents. And then we have three nodes that consider the taxonomy: flat H, flat W, and our own cat. And we use the same metric as before and the same subgroups. The outcome here is basically that cat performs best of our classifier, and also luckily for us that cat basically doubles the performance for rare concepts or concepts with rare examples, a few examples in the training data set. When we look at the Icarus, basically we have the same output. Performance is a little bit better because most of the time, we have more training examples than the other data set. When we now look at some quantitative results, here we have three example queries. We compute, we forward all the test images, and then we rank them by the probability predicted by our classifier for these three concepts. So first one, we have a female saint, 11H, Teresa. And you see that the top 5 are correct predicted. For the second one, Tower of Babel, here is everything is correct predicted. And then we have the concept 92C19217, so a very long concept, very deep into the hierarchy. And you see, for example, that the top 7 to summarize the project and to look to the future. Basically, here we introduce our new dataset Icarus. It's the currently largest dataset for icon class classification problems. We propose 3 strategy for synthesized image text pairs for contrastive learning. Basically, our vision language model approach with Blip achieves the best results, and we could outperform our baseline, the Rahnama 300M system. Then to our novel hierarchical multi-label classification CAT, we have shown that it scales up to the entire icon class taxonomy, and it performs all the other baseline that we consider in our experiments. For future work, we also want to expand the icon class annotation to non-Western art taxonomy, for example, the Chinese iconographic thesaurus. And currently, because this is a 2-step approach, we make the contrastive pre-training and then the classification training. We want to also combine them, so optimizing both lost targets at the same time. And then at the end, we also want to evaluate our CAT classifier on other hierarchical multi-label tasks outside of art domain. So thank you for the attention. Source code is available publicly.